about this particular topic, stress and strain diagram. Now let us have the repetition of these points once again. Now here we are going to take the stress values and here the strain values. Now let us consider one material, any one of the material. Now here if I go with the brittle material, we call this as the brittle. Now here yesterday I had given the example as glass. Okay. Now if I consider ductile material, okay, with an example as iron. Now, if I draw two diagrams in this particular single graph itself, now for the first brittle material, the graph will be like this. You are going to get a graph somewhat like this, and thereafter this particular point, if you reach the point here, so here the material will break into pieces. Okay, the glass will break into pieces. Now, if you compare the second material, okay, if this particular material is considered the ductile material, now the graph will have another path. Okay, it will go somewhat like this. Okay, and thereafter it is not going to break at a time. Okay, it will take certain time depending on the forces, and it may have maximum application of the force. Thereafter here it may break. Okay, so here the materials which are breaking easily under these stresses here, we consider those as the brittle materials. So example, I mentioned it as a glass. Now regarding the ductile material, so these materials, the ductile materials, will not break easily. Okay, so those will be having the deformation when compared with this particular glass. So let us have the extension of this ductile materials. Let us see about the ductile materials. Okay. Now here I will redraw the diagram. So I'm erasing the part, okay, entire part, and I will start the explanation for the ductile material with some iron. Okay. So for brittle, you are having a graph variation will be like this. So here the particular glass material or the brittle material will break into pieces. Okay. Now let us see about the ductile materials. Okay, now let us see. Now here we are going to take the strain. Now here if I start with the origin here, now the material, here we are applying the force. Okay. Now the corresponding strain will be plotted on the y-axis. I mean the x-axis here. Okay. Now here the stress is increasing and strain is also increasing. So up to, let us make this as point A. So between point O to point A, you are having stress, okay, proportional to strain. So here this particular region between O to A, you are having stress is proportional to strain. Now here, if I remove the forces, okay, up to this point I had applied the forces. So what actually stress here? Stress is given as force applied per unit area. So I'm increasing the forces here. Now as a result, you are going to get the increase in the strain also. Now after reaching point A, if I remove the particular forces here, now what happens? You will reach again to point O in the same path. Okay, so if this arrow mark is going in this direction, so if you remove the forces, then you will come back in the same path. So this particular property is showing that you are going to get the original state. Okay, you will have the original state, regaining of the original state. And this particular property is known as the elasticity. Okay, what is elasticity here? If you can go with the rubber band here, now here, if you are applying the forces, then what happens? If this is the length L, now due to the application of forces here, what you can expect? The length will increase. There will be increase in length. So this much part, let us assume there is an increase due to the application of two forces here. So this is the extended length, elongation here you got. Now this is the point. Let us go here up to point O to A. You got this property. Okay, so there is some elongation. Okay, now what I said here, you go back and you remove the forces. If you remove the forces, what happens? Again, the substance will reach its original state. Okay, the state of the original state will reach if you remove the forces. So that property we are considering it as the elastic property. So this is at O to A. So the reversible process. Okay. So between O to A, you are having the proportionality between stress and strain. So and this particular point will be considered as the elastic region. So this is a limitation you need to consider regarding the material. So we need to add a point here. Stress is proportional to strain, and here the property is there, and we are considering it as the elastic limit. Elastic limit. So between O to A, you are having the elastic limit. Nothing but you can, expect that the original state can be regained. So this particular property, we are considering it as a law here. Okay. So we call this as the Hooke's law. Hooke's law. So now, if you can repeat the same point, what you can expect here between O to A, you are having the obey of Hooke's law. Okay. So, and the region we call it as the elastic region between O to A. Now, if you can go with the extension, if you increase the forces beyond point A, okay, if you continue to increase the forces, what you can expect here, there will be some non-linear variation. So between O to A, you are getting a straight line here between O to A. So there is a straight line. So if you are getting a straight line means we are considering it as a linear variation. Okay, line, you are getting a straight line. So we are going to consider it as a linear variation. But here you are not going to get a straight line. So we call this as a non-linear variation. So between point A to B, it is non-linear variation. Non-linear variation here. Okay. So now here the Hooke's law, whatever you had explained here, that will not be obeyed between point A to point B. Okay. So here you will have partly elastic and partly plastic behavior of the material. What is the meaning here? Between A to B, if you had applied the forces, then what you can expect? The length will be elongated. Okay, there will be a change here. Some increase in the length will be obtained. Delta L will be there. Now here, if you remove the force, then what you can expect? There will be certain change. Okay, it is not going to regain completely. Okay, instead of regain completely, there will be certain extra length or elongation will be there. Okay, so here was the actual thing between A to B. Now, even after removal of the forces, it is coming back. Okay, it is trying to regain its original state, but some part is remaining here. Some extra part is remaining. So regaining this part is the elastic property. Okay, but here you got some extra property or the extra length here. So this is the plastic property. Okay, so what you can expect here between A to B, the material is having plastic property as well as elastic property. Okay, both these properties are exhibiting between A to B. Okay, plastic and elastic behavior will be there. So here the Hooke's law is not obeyed between A to B. Okay, now let us extend here what you can expect. So I will take another image. Okay, now see here. So from 0 to A, okay, we are going to get the elastic region here, and we can consider it as the Hooke's law is being obeyed. Now between A to B, okay, it is non-linear. Okay, it will be having both partly elastic property as well as plastic property. Plastic in the sense opposite of elasticity. Elasticity means regaining the original state. But here it is not going to get regaining of the original state. There will be certain deformation will be there. Some extra changes you can expect. So that's why you are considering this as the region where the Hooke's law is not obeyed. Okay. Now beyond point B to point C, or else you can do one thing. At point B, after reaching at point B, if you try to remove the forces, then what happens? There will be a graph going to reach the strain in this path. So earlier what you got from point O to point A, if you reach there and if you remove the forces, what you can expect? It is coming back in the original path. It is coming back in this path. But thereafter, after reaching point B, it is not going to come back in the same path. So it is going to take another path. Okay, if you can take here some B dash or B prime. So there will be some extra strain is remaining inside the material. So we call this as a permanent set. Permanent set. So there is a change in the length of the material that will remain as is. Okay, a small portion of the material will be having a deformation. Okay, we call it as a permanent set. Okay, now thereafter, if you consider between point E to point C, so here what you can expect, even though with small amounts of forces or the external forces, or even after removal of the force, if you can see here, here up to this particular point, you had applied a force. Okay, what is the stress here? It is force applied per unit area. Now hereafter, even though if you try to remove the forces, this particular strain is continuing. The x value is increasing here. Okay, the strain is increasing here. So here the deformation will continue. Okay, so that region we are considering it as a permanent deformation region here. Okay, so between B to C, you are going to get permanent deformation. Now thereafter, if you continue between point C to point D, this region we are going to consider as the plastic region. Okay, plastic region. So permanent deformation will remain permanent. Okay, so this is the plastic region. Now thereafter, if you continue here, now you can estimate what is this particular point. So this is the highest value of stress that is applied. Okay, you can refer to the graph here. So this is the highest value of stress. Okay, this is the stress here. So this is the highest value of stress. Okay, now here you can consider this as the ultimate tensile stress that can be applied onto the object or the material. So beyond this, what you can expect? If you continue here, if the stresses are same, then what happens? The material will start deforming. Suppose if you can assume this as a rod, let us assume this as a rod. Okay. Now if you continue to apply the same amount of force, okay, the same amount of force, okay, then what you can expect, even though after removal also, what you can expect here, there is certain change going on. The strain is developed inside the material. So here what you can expect here, this is the original state. Okay. Now due to the application of the forces here, we consider this as a part here. Let us consider this as a part here, some area as A. Okay, this is the area here. Now if you can compare here, what happens to this particular area means this area will start reducing. Okay, it will start reducing like this. There will be a reduction in the area. Okay, so the area is getting reduced. Now, if you still continue these amount of forces, or even though after removal of the forces, what you can expect? this area will start reducing. Okay, it will come to a particular point like this, somewhat like this. Okay, so we call this as the head formation. Okay, now thereafter, if you continue, what you can expect here, this material will try to break into some pieces, two pieces here. Let us assume it is going to obtain in the form of pieces. Okay, it is going to break. Okay, so this break point is obtained at point E. So point E will be considered as a break point. Here you are going to obtain the break in the material. So here, this is the thing you can expect from this particular concept, stress and strain diagram. So here what you are doing, you are taking a particular material. Okay, now how much amount of forces you can apply and up to what region the material is exhibiting the elastic property, and where you can estimate the permanent deformation is occurring. Okay, now here thereafter how much will be the highest stress that can be, or the material can be withstanding without any deformation or without breaking. Okay, that you can estimate. So those things can be expected with this particular concept, stress strain diagram. Okay, now here after finding these particular properties, where you are going to utilize this? That was the question. If I ask a question, what is the use of this particular stress strain diagram? Then what will be the answers? You can answer like this. You can find the elastic behavior of the material. Okay. Now here the point is reaching. If you can see here, this is the A point A. Now between these 2 points are what is the maximum stress it can withstand to exhibit the elastic property. Okay. Next here, where D is there, so it is a maximum stress where there is no change in the area. So if you consider at point D, this is at point D.
సార్
చెప్పమ్మా.
సార్ వాయిస్ బ్రేక్ అవుతుంది సార్
1 minute. ఏంటది? ఒక్క నిమిషం.
వాయిస్ బ్రేక్ అవుతుంది సార్
వాయిస్ బ్రేక్ అవుతుంది. ఇప్పుడు ఓకేనా? హలో.
ఓకే సార్ ఇప్పుడు
ఓకే. Okay. Now here these things you can consider. Now, meanwhile, this point C can be considered as a yield point. The point C we are going to consider it as a yield point. Now, what is the yield point means? You can refer here. Yield point is a point here. Even though if you remove the load, okay, there will be certain changes that will continue. So what you can expect regarding this point means, let us assume you are hanging a material. Consider this as the iron wire. Okay. Now here there is some disc which is hanged. Now if I increase the weight of this, or suppose let us take this is the length some 10 centimeters. Now if I apply some 10 kg, there is some elongation. Let us assume you are expecting the elongation of some 2 centimeters. Now if I increase this weight to some 20 kgs, this particular elongation, extra part, may be some 3 centimeters. Now thereafter, if I go with 30 kgs weight, you can expect some 5 centimeters, for example. Now thereafter, I am not going to increase this particular mass. Okay. Then even though I had stopped this particular stress, there might be a change. You may expect some 5.1 centimeter. Initially it was 5 centimeters. Okay, increase due to the application of 30 kgs. But hereafter, if I stop increasing the weight, this particular deformation is continuing. So here you may reach some 5.1 centimeter in excess. Okay, so this will continue. If you continue here, then you may expect some 5.2 centimeters. I'm not increasing this particular weight. So I stop at the weight here. Now that the thing you need to consider here, that point is considered as the yield point. Okay. Now, what are the important points regarding stress and strain diagram? You are going to consider the materials, and depending on the variation between stress and strain, first point is that you need to find whether the material is brittle or ductile. So what is the meaning of brittle here? So here the materials which can break easily. Example is glass. Okay. Now here regarding ductile, so those are not going to break easily, but they are going to obtain certain elongation inside the materials, or deformation will be there continuously if you apply the forces. Now, example here, I had given it as some iron as the ductile material. You can take aluminum, you can take copper, and certain other materials. Okay, so first thing is that you are going to identify which one is brittle and which one is ductile material. Now, thereafter, if you consider one material, any one material, you can find where is the elastic property exhibiting, up to which point you can obtain the elastic property. Okay. Next, thereafter, where you are expecting the multiple in the sense both elastic and plastic behavior. Okay. Thereafter, you can estimate even though after removing the forces, you are having the elongation, and due to that, you are considering y as the yield point here. Yield point here. Now, if you go beyond these particular points, what you can expect? This is a plastic region. Plastic region in the sense you are going to get permanent deformation in the material. At point D, this is the maximum stress that is to be considered. Okay, because the graph is not going beyond this particular point. So this is the highest point on y-axis. So what is there on the y-axis? You are having the stress. So this is the maximum stress that can withstand by this material. So this particular D can be considered as a ultimate tensile stress or tensile strength. Okay, anything. Now beyond this particular point D, what you can expect here, the material is going to get a change in the area, a small part or anywhere on the particular material, certain area will be reducing. And if you continue the same state, what you can expect, this area will still continue to reduce, and thereafter it will break into pieces. Okay, so you can find where is the break point and what is the maximum stress that can be applied on the material. So these points will be considered as the uses of the stress strain diagram. I think you might got a clear idea about this topic. So main thing is that you can characterize what is the character of the material, whether it is brittle or not. So how much stress can be applied? What is the maximum stress that can be applied? So between which stress it is expected as a elastic property. Okay. So those things you can expect from this topic, stress strain diagram. So depending on this, the main thing is that if you can go with one example, okay, the real time application here. If you are going to construct a bridge here, you are going to construct a bridge, okay, you need to find which material can withstand more stress or more forces. For that, if you can see here, if you are considering steel as the best material. Now, if a steel is going to, if you are considering a material in the form of wire or some rod like this, okay. Now here, if this particular material can withstand up to some 100 kgs of weight for this particular example, okay. But in the real time, experimentally, you know from the graph, okay, after the experimental facts, okay, if you found that 100 kgs is the maximum weight that can be applied, then in the real time, you need to apply only 10 kgs. You should not go beyond this, okay, to avoid destruction. The limitation has been given by the government, okay. So here, if you can see, you are going to use some ISI marking on the products. Similarly, if you consider what is ISI, Indian Standard Institute, okay, Now, depending on those standards, while constructing or while the applications in the application part, if you found certain value, you need to take only 10% of that particular value under the application. Okay. Now here, if this particular material is there, let us take one rod. For this particular rod, we are having maximum limit of the force that can be applied, the weight that can be applied is 100 kg. But in real time, you are going to use only 10 kg as a limit. So now here, if you are having a load of some 100 kg, if you are having a load of 100 kg, so now how many rods can be used here? You need to apply 10 rods. If the load is 100 kg, you need to apply 10 rods. Okay, so 10, the number should be 10. What is the reason here? For each rod, even though it can withstand up to 100 kg, you should not use single rod. Only 10% of that particular maximum value that should be considered. So here for one rod, we are going to consider only 10 kgs as a limit. Okay, but you need to get 100 kg for this explanation here. They are considering 100 kg as a load. Then you need to have 10 into 10. So 10 rods should be utilized in the real-time application. Okay. So how you are going to find this as a 100 kg here? Okay. So those things will be obtained by the stress strain diagram or the experimental facts. Okay, that is about this stress strain diagram. If you are having any doubts, you can raise, or else I will continue with another topic. I will give 2 minutes time. If you are having any doubts, you can raise your hands. Or else you can chat in the, send in the chat box. So we are referring the stress and strain diagram. If you are having any doubts, you can raise, or else I will continue with the next topic.
No doubt, sir.
Okay, now what about other members? Okay, 103 said no doubts. Okay, no doubts regarding 103. Okay, meanwhile, I will take paper here. If you are having any doubts, you can raise your hands, or else you can send in the chat box. Okay, now the next topic we are going to see about the elastic constants. Okay, now this is a topic we are going to see. Now, instead of these elastic constant, you can call on these as elastic moduli also, or modulus of elasticity. The same topic can be considered as modulus elasticity. Or if there is only one, then you will call it as modulus. If you are having more number of modulus or moduli, we are going to consider. Okay. If there is more number of modulus, okay, then we will call it as a moduli of elasticity, plural form. Now, what actually elasticity or modulus of elasticity? Let us go with this. Now, previously regarding Hooke's law, we know that stress is proportional to strain. Okay, both these two are proportional. Now let us refer back to the Hooke's law, and we will find what is the modulus of elasticity and why you are getting different types of modulus of elasticity. Okay, or moduli. Now let us see here. Now what was the Hooke's law? Hooke's law states that stress is proportional to strain. Okay, it is directly proportional to strain. Now if we remove the proportionality, you are going to give a constant, some constant. I will take some E as a constant, okay, into strain. Now here E can be given as stress by strain. So here E, we are going to consider this as the modulus of elasticity. Modulus of elasticity. Okay, some message I got here. Okay, stress by strain is E. Okay. Now here, by using the Hooke's law, we will continue the topic and we will find elastic constants or moduli of elasticity. Now, how we are going to continue means, let us consider about the stress. Now, previously we had seen a concept, the different types of stress are there. What were those? If you are considering a material, if a material is there, and if this is the axis of the material, if you are applying two forces like this, then you are going to get a variation in the length. And this particular variation in the length, we call it as a longitudinal stress. Longitudinal stress. And the corresponding change in the length, we will call it as a longitudinal strain. So by applying these two forces, you are going to apply the longitudinal stress. So what is the reason here? The force is given as, I mean, the stress is given as force per unit area. Now the result here, there will be a elongation. So it is occurring in the straight line here, this particular direction. Okay. So that's why it is also longitudinal. So here it is considered as a longitudinal strain. So here in this concept, we are going to consider longitudinal stress by longitudinal strain. Okay. So this was given by the scientist Young. So that's why we will consider this as Young's modulus. Young's modulus. Okay. So this was given by the scientist Young. So what was the concept considered? You are applying a longitudinal stress. What is the meaning of longitudinal stress? This is a diagram. You can expect what is going on here. So on the object or this particular material, you are applying two equal and opposite forces in these directions. Okay. So now here it is in the form of a line. You are going to get it in the form of a line here. Okay. So we call it as a longitudinal stress. And again, the change is going to be occurred in the same line. So it is again, it is the longitudinal strain. So according to Hooke's law, you are going to take stress by strain. So here, what type of stress you are applying? Longitudinal stress. And what is the result here? You are getting the longitudinal strain. So if you take the ratio between these two, we will consider it as a Young's modulus. So here it is modulus of elasticity. Okay. Now here we are considering it as a Young's modulus. Take this as some y. Okay. Now how can you give the stress? Stress can be given as force per unit area. Okay, the numerator. Now what is the longitudinal strain here? Longitudinal strain is given as change in the length, change in the length, okay, for the in divided original length, original length. Now, what is the meaning means? Let us take this particular diagram here, this diagram. Now, let us consider initially the length is L, some 10 centimeters, 10 centimeters, for example, 10 centimeters as our length. Now, here, due to the application of force or the stress here, what you got some elongation. Now, the result is some, let us consider, got some 15 centimeters. Now, you can divide this, I mean, the concept can be like this, 10 plus 5 centimeters. So some 5 centimeters elongation you got in extra. So now how can you write here? L is the original value plus some delta L. Okay, so what is the delta L value? It is 5 centimeters. So what is delta L? It is a change in the length. So now what is the change here? It is 5 centimeters. Okay, change in the length is a 5 centimeters. What was the original length? It is a 10 centimeters. Okay, so here centimeter will get cancelled and the value will be 0.5 for this case. Now instead of these values, you will take the equation. What is the change in the length? It is delta L. Okay, take the delta L value. Now what is the original length here? It is L. So take L here. Okay, now what is the longitudinal strain? Longitudinal strain is delta L by L. Now you substitute here. Substitute here delta L by L. Now what you are going to obtain regarding Young's modulus? So Young's modulus is written as capital Y, let us take. Okay. Now it is given as stress. What type of stress? It is a longitudinal stress by longitudinal strain. It is delta L by L. Now you can rewrite this as F by A. Okay. Now into delta L, and this particular L will come back to the numerator. So we will write like this. So what is the result here? Y equal to capital Y. So F L by A into delta L. So this is the Young's modulus, okay, that is obtained due to the longitudinal stress. And what you had obtained, you got longitudinal strain. Okay, so this is the Young's modulus. So what is the thing you need to consider here? You are applying the force or the two forces here on a line, okay, on the axis here, whatever the thing you are considering here. Now let us go with the second concept. I mean, second constant. Okay, now let us take a material. Now consider this as a three-dimensional diagram. Okay, now continue here. Okay, now here this is the material. Now this is a three-dimensional diagram. If you consider this as L length and this has some breadth B and this has height H. Now if you take the product of these three, then what you will get? You will get this as the volume. Okay, so entire volume you are considering. Okay, now instead of this, you assume you are having a sponge. Consider you are having a sponge in your hands. Assume this as a sponge. Consider this as sponge. Now, what we are going to do? So, what is the concept here? We are going to get the second elastic constant. Okay, second modulus of elasticity. Okay. Now, here you apply forces in different directions at a time. At a time, you try to apply different forces. Then what you can expect? This particular sponge will become like this. So, what is there? If you consider now, here this value is some L1, L2, L3, something you can take like that. Okay, L1 some 10 centimeters. Now here height as some 5 centimeters. For example, I'm giving, and B as some 5 centimeters. Now what happens in this particular concept after applying the forces? The length will reduce. Consider some you got some 5 centimeters. So instead of 10 centimeters initially, there is a reduction in the length. Similarly, the height will also reduce. Consider some 2.5, for example. So it has also reduced. Now again the breadth. Okay, again let us consider some 2 centimeters. So there is a reduction in the entire values. So if you consider now this has some volume V1. Now here consider the volume as V2. So now what you can say here, V1 was greater than V2. Okay. So here after applying the entire forces here at a time in the bulk form, okay, then what you are getting? You are getting a change in the volume. Okay. So this particular concept is considered as bulk modulus. You are going to get the bulk modulus. It is going to give the bulk modulus here. So here, what is the stress here? You are going to get volumetric stress. You are applying the volumetric stress, and as a result, you are going to get volumetric strain. Okay, or else you can consider the same thing as bulk stress, bulk strain. Okay, so the same thing you need to consider, and here this modulus going to consider as a bulk modulus. So here again, you can give the volumetric stress. Stress is nothing but force applied per unit area. So the same thing, force applied per unit area. Now again, you go back here. So if V is the original value, and here V has been reduced, there is some reduction. Consider the value has been reduced in some delta V. Okay. So now here this is the original volume, and this is the resultant volume after the application of the stress. So the same thing here you can consider here the change in the volume per or the divided by original volume. So you can substitute here F by A delta into V. So this particular concept will be considered as the bulk modulus. Okay. Now let us go with the third type. Third. So totally you are having three modulus or moduli. So what is the third? Now here let us take the diagram like this three-dimensional diagram. Three-dimensional diagram here. Now what we are going to do? I'm going to apply a force on the surface. Okay. Now the same thing here, consider the sponge, whatever the sponge is there, consider the sponge. Consider the sponge here. Now what you are going to do, you try to apply the force in this direction on the top, on the surface of this. Okay, on the surface here, like this. Okay. Then what you can expect, the sponge at the bottom will remain as is. Okay, you can expect the bottom will remain as is. But here you are going to get the deformation in this form, like this. The sponge going to be rearranging in this direction like this. Okay, so this was the initial direction. Okay, if I want to draw the same thing in the single diagram, I can draw a dotted line like this. Let us draw a dotted line like this. Okay, and here you will get a dotted line like this, and here also the dotted line like this. Okay, now this is a result of application of the stress. So here between these two, black and red. We take this as theta. Okay, we call this as the shearing angle. Shearing angle. So here you are applying a force. Okay, now due to that you are going to get a shearing angle. Okay, but the thing is that the shape of this particular object is remaining as is, even though you are having a change in the shearing module or this particular concept. Okay, so now here, what is this? You are going to get this as the tensile stress. You are applying this as the tensile stress, and here the strain is considered as the shearing strain. Okay, this angle is considered as a shearing angle, and the stress is considered as a shearing angle. Okay, now how can you write the law? It is now written as tensile stress by shearing angle, or sorry, shearing stress. Okay, now here this modulus is known as rigidity modulus. Rigidity modulus. Okay, consider the symbol as eta. Okay, now again, if you want to write the formula, it is force applied per unit area, and here you consider this length, this length as L. Okay, and if you can redraw here, let me do one thing. Consider this as the original length L, and how much it has moved. Let us consider this as delta L. Okay, so now here you are going to take those two factors. Now take the change and divide it by original. So this will
Hello,
be the
sir.
expression for the
Hello.
rigidity modulus. Chepama.
Hello, sir.
Hmm.
Tensile stress by shearing strain, sir.
ఓకే. ఓకే. ఇక్కడ తప్పు పడిందా? ఓకే. హ్మ్.
Okay, sir.
దిస్ ఈస్ స్ట్రెయిన్. So this is strain as it is. Okay, we started with stress by strain, so that will remain as it is. Okay. So now here this is the expression for the rigidity modulus. Rigidity modulus. Now this particular rigidity modulus, we will do the experimental fact also. You are having one experiment. Even though in the theory also, you are going to see the particular verification of rigidity modulus, and there is an experiment known as a torsional pendulum. We are going to see a topic as torsional pendulum. So this is the experiment. This is experiment to find the rigidity modulus of this material, whatever may be the material. We are going to construct a pendulum. So there you are going to utilize the tensile stress, and you will do the experiment, and you will find the result as the rigidity modulus. So now here, what we had seen today, you had seen about the stress strain diagram and its applications. Okay, depending on the explanation. Thereafter, we had seen the Hooke's law in order to find the different types of elastic constants. Now, what are the constants available? Now you can answer here. You are having Young's modulus, Y. Next, bulk modulus. You can consider it as K or B. So I am considering it as K. Next, the rigidity modulus. So it is eta. So what were the formulae? What you wrote? The formula will be remaining as is here. Okay, it is F by A by delta L by L. Okay, you can rearrange those. Okay. Now here, regarding bulk modulus, you will consider the volume. So stress is force applied per unit area, and here the volumetric change or the strain is delta V by P. And here again force per unit area and change in the value due to the shearing by the original. So these were the three moduli depending on the different types of stress and the strain experienced by the material. Okay. Now, are there any doubts? Okay, you had given certain answers. Delta L by okay, L. Okay, if you are having any doubts, you can ask.